All right, taking a look at notes I handed back yesterday, or handed out yesterday. Um, Centripetal force, we've talked about centripetal force. Centripetal force can be calculated by mass times the velocity, tangential velocity squared divided by the radius. Okay, the force keeping the object in a circular path is a friction. Okay, is friction string. When we talk about centrifugal, not centripetal, centrifugal force, it's the outward force felt on an object in a circular path due to inertia. Okay, it's what we talked about before. The idea of inertia, when a car is going around a curve, we have a car that's going around the curve. Well, all the objects that are sitting in there want to follow the idea of inertia. Okay, which means they want to continue on in a linear path as they go along. Well, the car, as it moves along, is going to continue by friction, maintain the circular path. But the objects, once again, they want to continue in a linear path because that's what inertia is going to tell us to do. So that centrifugal force, which is not a calculating thing, but it's a force that pushes people that are going in a circular path outwards. Planets travel an elliptical orbit around the sun. This orbit is nearly circular. What forces keep them circular? As we talked about yesterday, this in Kepler's ideas and Kepler's laws and Tycho Brahe, this orbital path is close to being circular. It's not perfectly circular, but it's close. It is an elliptical path. And once again, the force that keeps it going in the circular path, as we talked about yesterday, is what? What keeps the orbits in the circular path going around the sun? Gravity. Yeah. The gravitational pull between the planet and the sun. But all the planets and all the moons, they have gravitational pull. And they all work in sync with each other to make sure that we maintain our orbit that we go around the sun. If you would take all the planets away from the universe and just put the Earth there in the universe, the Earth would not be in the same orbit because there's a small gravitational pull between Pluto and the Earth, between Mars and the Earth. Okay, so there's a slight gravitational pull that's there that keeps us going in the path that we are going in. If we would take a look at, say you have a supersonic gun that could shoot a bullet from the top of the top of a cliff. and you can shoot it at such a velocity so that, well, if I just shot a bullet from a gun, it would eventually land on the ground. And that's just projectile motion. But if you shoot it fast enough, when it starts falling, and the reason why it falls to the ground, because the earth has a gravitational pull that pulls the bullet down to the ground. So gravity is going to pull this bullet down to the ground. But if I shoot it fast enough so that when it starts to fall to the ground's not there. Because we've shot it far enough out there, when it starts to fall, the round earth that we live on it starts to fall but misses the earth. So what happens is it keeps on traveling and it keeps on missing the earth. If you could shoot a bullet fast enough, it would launch out so far that it would miss the earth as it starts to fall to the ground. If I throw an object right now, I have a projectile motion, it's going to fall to the ground. But if I would launch that projectile fast enough so that when it starts to try to hit the ground is no longer there, what would happen is it would just keep on traveling around the earth. I mean, you travel around the earth. And what would happen if you have no gravity there? If you shoot it, it would hit you in the back of the head. The bullet would hit you in the back of the head. That's theoretically not really going to happen. But we utilize this idea when we start talking about all the satellites that are up above us. Satellites orbit around the world. They orbit around the world. Okay, they keep moving around the world. And the world keeps spinning also. It has to have a velocity, an initial velocity, that will keep it moving. And you need to have this velocity so that it won't fall to the ground. Eventually it runs out of fuel and it will fall to the ground. But this is the idea of a satellite right here. This is what happens with a satellite. You get a velocity with respect to the satellite fast enough, the attraction to the ground, the earth still has an attraction to it. When it starts to want to fall to the earth, it misses the earth. Sir Fig of Isaac Newton, he theorized the gravitational force between two objects is directly proportional to the product of the two masses and inversely proportional to the square of the distance between the two masses. Newton theorized the gravitational force between two objects is directly proportional to the product of the masses. And inversely proportional to the square of the distance between the two masses. So there's gravitational force between masses. Okay, you're between two masses. It's gravitational force. This is a symbol. It's a circle with two lines that come out. That means directly proportional or proportional to the product of the two masses divided by the square of the distance between the two masses. So we have this gravitational force is equal to some constant K times mass 1 times mass 2 divided by r squared. And this is a proportionality constant. Sir Fig of Isaac Newton couldn't figure out what the constant was. He couldn't figure out what the constant was. So the next guy that came along was named Henry Cavendish. Henry Cavendish. He came in 100 years after Sir Fig of Isaac Newton and verified Newton's theory and measured the proportionality constant. He was able to measure this proportionality constant. And how he did this is just ingenious. He had a string, and he had two smaller lead balls on the end of the stick. He had a stick here, and he had lead balls at the end of these. And then he had two bigger masses that were lead balls out here that he had positioned, and this string would start to rotate towards these masses here. These smaller masses and the string would rotate towards these bigger masses. So what Cavendish did, he measured the amount of force required to rotate the mass of the string through a given angle. Then placed a large mass, lead balls. Cavendish measured the amount of rotation comparing the force to the forces first measured first. He then was able to calculate the proportionality constant. So through this experiment, he was able to measure this proportionality constant. And this proportionality constant is equal to 6.67 times 10 to the negative 11th Newton meters per kilogram squared. When you're calculating the distance between two objects, you measure the center of gravity, or from the center of gravity. For spheres, it would be the measure of the center of the spheres. So you're measuring from the center of gravity. Okay, you just don't do outer edge to outer edge. Okay, you look at center of gravity for one, you look at center of gravity for the other, and you measure that distance. All masses have gravitational forces between them. All masses have a gravitational force that's between them. You sitting beside another student, there is a gravitational force between you two that's pulling you two together, 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 that's pulling you guys towards me and me towards you guys. Now, our masses are very small. Our masses are very small, and the distance is not very large. Okay, so our gravitational force that we feel between us is minimal. But you always think about that, that magnetic attraction between people that you have. Okay, well, there is something physically and science-wise that says there is a gravitational force that attracts one person to another person. It's just how physics is. We just don't feel it, okay, because it's so small. Okay, it's because there's gravitation. Think about our masses. Okay, our masses are not that great. Okay, you're talking about kilograms, we're talking about 60, 70 kilograms. Okay, we're multiplying 60 and 70 kilograms. Our distance that we have between us is very small. Okay, but we're multiplying that value by 6.67 times 10 to the negative 11th. Okay, so we're taking like 420 divided by distance, taking the value 200. We're taking the value of 200 and multiplying it by 6.67 times 10 to the negative 11th. Okay, the kilograms and the meters would cancel out, and that would give us our newtons. That's not a very strong attraction because it's times 10 to the negative 11th. That would be times 10 to the negative 9th would be the number of newtons that we are attracting. So it's very small, but we do have, us having masses, there's an attraction to us. Okay? There's an attraction to us. If we would stand on a desk, okay? If we would stand on the desk, hopefully I don't kill myself. Okay? If we stand on a desk and I would jump off the desk, okay? If I would jump off the desk, there's a gravitational attraction of me going to the earth. But there's also a gravitational attraction of the earth coming towards me. Which one is it? Am I going towards the earth, or is the earth being attracted to me and coming to me? Because for every force, there's an equal but opposite force. going in the other direction. Gravitational force between planets, moons, and the sun all keep us in a nearly circular path. If so, then these forces are centripetal forces. Newton's third law indicates all forces between celestial bodies have an equal but opposite force. Gravitational force between planets and moons and the sun all keep us nearly circular. If so, then these forces are centripetal forces because they are keeping us in a circular path. The idea of what keeps things in a circular path. Well, there has to be a centripetal force there that keeps things in a centripetal in a circular path. And Newton's third law indicates that all forces between celestial bodies are equal but opposite. So the pull that the Earth has on, or the moon or sun has on us, we also have on the sun. The moon that goes around the Earth, there's a gravitational pull between the Earth and the moon that has to be equal but opposite. Because if they weren't equal but opposite, if the centripetal force from the Earth to the moon was greater, the moon would collide with the Earth. If the force from the Earth was greater than the force coming from the moon, then the Earth would pull the moon into our atmosphere and collide with the Earth. They have to be equal but opposite. I don't know if the Big Bang Theory is still out there. I don't know if you ever watched it or not. Raj on the Big Bang Theory was an astrophysicist. This is what they do. This is their world in the idea of astrophysics. Okay, you are looking at planetary motions and what is occurring with planetary motions, but not just just not within our universe. They're looking for stars outside of our universe and suns that are stars outside our universe. And what effect does that have? Does other universes have on our universe? The gravitational force of attraction between a large object and a small object cause both to accelerate. Objects falling to the Earth are also falling, the Earth is falling towards the object. Once again, me jumping off the chair and not breaking my ankle, it was a positive thing. But I'm being attracted to the Earth, but the Earth is also being attracted to me. It's coming towards me. But the mass of the Earth is so massive compared to my mass, okay? It's not going to be, the Earth is not going to move that much. It's not going to move at all because that mass is bigger than my mass. How do ocean tides work? been to the ocean before? Okay. Do you like high tide better or low tide better? High tide. I know I like high tide better. Why? The waves are bigger. Okay. You go to the ocean and it's low tide. The ocean's out a little further, and the waves aren't very big. It's not as fun. Get high tide, man. You might get some big waves coming in there. That's more fun. Well, what causes high tide and low tide? What causes that? Anybody know? It just happens every about 11 hours or 13 hours. It just shifts. Anybody know what causes it? Every 6 hours, high tide to low tide back to high tide. It's a periodic function. It's the moon. The moon, the phases of the moon causes your high tide and low tides. Well, what happens when the moon is here? Once again, you have this gravitational force between the Earth and the moon. The moon's going to go around the Earth here, it's going to go around the Earth. It's going to orbit the Earth. Okay, we have a satellite there. Well, we have this gravitational force that's going between them. When the moon is over top of you, what it's going to do, it's going to pull water towards it. It's going to pull water towards it, which means there's going to be more water here. If there's more water there, that's going to create your high tide. Okay? And the direct opposite, when you're totally opposite of that, you're going to create this high tide. Water's going to rush to here. When the moon comes over here, the water is going to rush towards the moon. The reason why is the moon has a gravitational force towards it. It's going to pull the water towards it. When it pulls the water towards it, you're going to increase the level of the water, which gives you the high tide. So when you want to take a look at the phases of the moon and where the moon's at, okay, when you get the moon that is there over top of you, you can see, do I have high tide or do you have low tide? Okay, so and the moon continues it continues to go. The world keeps on spinning around, the moon's there. You're going to have that gravitational pull between the moon and the Earth, and it's going to pull the water there. Okay? Which, if it pulls the water there, it diminishes the water over here, which gives us your low tides. So your high tides and low tides is basically your gravitational pull of the water to your area. What is the gravitational pull of the water towards your area? That will give you the high tide. The water is rushing towards your area. If the water is rushing towards your area, that's going to create some higher waves for you. If the water is rushing away from your area, that means it's pulling away, then your waves aren't going to be as big. We go down to Daytona Beach all the time. In Daytona Beach, you have the high tide and low tides. It's very dramatic where the water level is on the beach, where the beaches are on the beach. Where you have the water level coming up to on the beach. If you go down during low tide and put all your towels and everything and umbrellas and chairs down closer to the ocean, and it's sitting there during low tide, okay, when high tide comes, you're going to get overran by all this water. And there's a distance of, I bet you, from high tide to low tide, a distance of about 30 yards for where the water comes to. When it is low tide, the water is way out. Okay? When it's high tide, the water comes in, I bet maybe 25 yards. It comes in 25, 30 yards, and then it will go back out. And if the high tides, if the moon's in your area, the high tides are going to be greater, which means the high tides will sometimes come up to where there's a break wall there. They'll come up to there because the high tides are so high. So all of your ocean tides are based on the gravitational pull of what the moon is, because the moon is going to pull things, okay? And the water is an easy thing to pull. On Monday, what we'll do is we'll finish up the notes. We'll compare the force of gravities that we have here. Our force of gravity using our constant. We'll compare that to, because this is our centripetal force, this is our force that maintains our circular paths. So we're going to set this equal to our centripetal force, which is our b squared divided by our mv squared divided by r. And we'll see what we come up with that. All right, rest of the time is yours. I've lost my voice.